So the next speaker is Professor Vinaychandran from CAOS. So if you want to meet him, go downstairs.
Good afternoon, everybody. So my talk is on ocean modeling. So what I have included today is snapshots from the work that we have been doing on ocean modeling, particularly focusing on the Indian Ocean. So our objective for a long period has been to use the model to understand the basic processes that's going on in the Indian Ocean. So in that philosophy, the requirement for the model performance is not as stringent as one would expect in a model that is required to produce actual forecasting. But recently there has been increasing demand to simulate the realistic fields in the ocean, both from industry as well as from research community. So we have also been trying to improve the model to produce better simulation. So we also try to do a little things using data assimilation quite some time back, but haven't made much headway in that. So I will also share you a couple of slides based on that. And our entire research is funded by Ministry of Earth Science through INCOIS, so I should thank them. I should also thank both Ravi and Amit for giving a chance to come here and talk to all of you. So that's a picture of COS. That's before this block was built. So anyway, so something that is central to ocean dynamics is an argument between a coffee cup and oceans, which is deeper. So scientists have taken the side of the coffee cup because they know that it's only with coffee that they can attack the problem of understanding ocean dynamics. So what we do usually is assume that the length scale of the oceans are much larger than the depth. So it's basically and essentially a shallow water system. And other basic principles that are involved are that its oceans are a rotating system. That basically makes a difference between many fluid dynamics applications that you see in engineering. It's stratified, and this has a large effect on different parts of the Indian Ocean. It's basically turbulent fluid, and it's driven by mechanical energy supplied by the winds at the top, and also by heat and freshwater fluxes from the top. Then something that is of consequence is to many atmospheric process is that it has high heat capacity. The specific heat of oceans is about 4 times larger than that of the atmosphere, and then it also has a long memory. And then once you put all that kind of physics into equations, you have basically the Navier-Stokes equations. The actual equation that we solve in the model is in slightly complicated coordinates, but what I have put here is the simple equations in Cartesian so that it's easier to understand. So these are the set of equations. We have U momentum equations. The first terms are the acceleration, and the second is the effect of rotation, pressure gradient, and the 3 terms on the right side is for mixing both horizontal and vertical. A similar equation for V momentum, and the third equation reduces to a hydrostatic equation because of the assumptions that we have taken. Equation of continuity for the incompressible fluid, and an equation for temperature and salinity, which is related to the density and feeds back onto the momentum equations. So one has to discretize these equations onto the surface of the Earth, decide the size of the grid, and also stack them vertically, and then you basically have an ocean general circulation model. So the model that we have basically used is the popularly called as MOM, and it has different versions starting from MOM 1, and what's in being developed right now is MOM for P1, and this is based on MOM for P0. So we have configured this model for the Indian Ocean. So we have the complete Indian Ocean domain, and the southern and eastern side is open. So that's a little bit of a problem. So there what we have something is called a sponge, where we relax the conditions back to the observations with a time scale that is suitable for the physical situations inside the basin. So the idea is that things happening at the boundaries do not affect the regions where you are interested too badly. The resolution of this model is approximately 25 kilometers, which was fairly high when this model was initially set up almost 5 years back. And at present we can do much better because the computational power has increased tremendously. And because the stratification of the Indian Ocean is very strong and it has to be resolved well, we also need to have fairly high resolution in the upper layers of the ocean where things are changing very rapidly. The rest of the configurations are standard, widely used in ocean general circulation models, and such a model is driven by the winds at the surface. That this wind stress provides mechanical force, and the shortwave radiation is prescribed, and then rainfall and river discharge are required to calculate the dilution and its effect on the salinity, and then air-sea fluxes. Due to interaction with the atmosphere, you require humidity, temperature, and winds. So something remarkable about the Indian Ocean is monsoons. You might have heard it in the lectures in the classes. So the main forcing that we apply to the ocean is time dependent, and they keep changing from one direction during summer to the other in winter. So they the winds blow towards India during summer and away during winter. So, and because of the monsoons, the properties of the Indian Ocean have stark east-west contrast. So for example, if you look at temperature, the eastern side of the ocean is very warm compared to the western side that you see during both summer and winter. In addition, the salinity of the Indian Ocean is very low on the eastern side and very high on the west. This is because since the temperature is higher on the eastern side, most of the convective systems are also located on the eastern part compared to the west. So most of the rainfall that you receive is on the eastern side, and most of the rivers that are sitting on the Indian subcontinent discharge onto the eastern side. Therefore, you have very fresh salinities on the eastern side and very high salinities on the western side. And this is somewhat typical of the Indian Ocean. So the ocean models which were developed then did not have this capacity to simulate this well. So this was done by my student, and he did a good job of including river discharge into this ocean basin so that it can simulate the flow of fresh and saline waters to the either side of the Indian Ocean as a function of the seasons. So you can see how the river discharge, the Ganga-Brahmaputra water flows down along the coast of India, comes around and comes in both into the Arabian Sea and remote locations of the Indian Oceans. This is, well, so I haven't put much on the process studies for this talk, so I would like to show a couple of slides on how good such a model is vis-a-vis observation. So this is a sample for the year 2006. So 2006 was a kind of unusual year because the Indian Ocean developed a pattern of anomalies marked by large departure of SSTs towards the negative side on the eastern part of the Indian Ocean, and western side, warm anomalies on the western side. What you see here is departure of the sea surface temperature from its long-term mean. So all the red patches, the temperatures are unusually higher by the magnitudes that you see here, and on the eastern side it's cooler. And this has a lot of implications to the atmosphere because it can affect the patterns of rainfall. Typically, if this happens, Indonesia and Australia receives less rainfall, and on an average, India receives better rainfall. So therefore, this phenomena, which is called as Indian Ocean dipole or equatorial Indian Ocean oscillation, has received a lot of attention in the past. So the oceans do play a very active role in this process. So it's very important that the ocean models are capable of simulating this process very realistically. So this is an example of how good the model is. So on the left hand side, you have the simulation by the model, and on the right hand side you have actual observations from satellites. So you can see that the model is capable of reproducing the patterns well. However, there are differences. You don't get the magnitudes as much as you would expect, and also there are differences in particularly on the western side. So there is a scope for improving the model further. Now this is another example. This is an example of the velocity field. This is the red curve in this picture is from observations, and the black is from the model. And what you see is a graph of the zonal velocities. That's a u component. So if it is positive, that it is towards the east, and if it is negative, it is towards the west. And this is the observations are measured at this location in the central part of the Indian Ocean. So you can see that if you look at this model output, it gets the large scale variations of the currents pretty well, and the best comparison that you would see is close to the surface. However, there are certain occasions when the model and observations differ, and particularly in fluctuations like this. So there are departures of these models from the observations. Now in models such as this, you can have departure from between observations and simulations basically for three reasons. One is that the model itself has physics which is unresolved. A good case there is mixing, which is very little known, particularly in the verticals. That's why you would see all the momentum that you put at the surface has to be distributed appropriately as a function of depth. So therefore you can easily see that the differences between model and observations somewhat grows as you go deeper. So there are similar issues also associated with horizontal mixing, and then the rest is due to the assumptions that we have taken when we have written the basic equations. And secondly, there are unresolved length scales, because when you map the equations to a grid, you compromise on the length scale that you can resolve. I will come to a little bit of detail on that later. And finally, these models are forced by observed atmosphere. So any deficiency that you have on your observed wind field, or observed air sea fluxes, or observed freshwater and river discharge can have its own impact onto the simulations. Now coming to the length scales, there is a large spectrum of scales that is associated typically with ocean motions. So the largest is associated with the overturning circulation, where the cold water sinks in the polar region, goes deep into the ocean and surfaces near the tropics, and then that water is circulated, which is called as global thermohaline circulation or the conveyor belt. And then when we come to basin scale, there are these large scale gyres which covers an entire basin, such as the northern Atlantic and northern Pacific, or any other parts of the Indian Ocean. Those scales are basin scale. Now even when we come down to smaller scale, we have eddies which are much smaller, probably 100 kilometers in both directions. So the fundamental length scale that we would like to resolve is defined by a number called as Rossby radius of deformation, which is based on the stratification of the ocean and the dominant modes that is propagating across the basin. So if you look at the Indian Ocean, you can see that those numbers go to, this is in kilometers, this is the Rossby radius map of the Indian Ocean, and the calculation is slightly different for the equatorial region and away because of the difference in the dynamic, the way the dynamics of rotation affects the tropical and extra tropical regions. So if you plot it just away from the equator, you will see that for the northern part of the Indian Ocean, which we are interested most, we get a number of something like 40. And this is a simplified graph of that. You see that the Rossby radius of deformation decreases as you go away from the tropical region. And the latitudes that we are interested in, it comes down to about 40. So if you need to resolve them, we need something like 4 grid points. That means you need a model of about a 10-kilometer resolution so that you can resolve the large-scale dynamics fairly well. So this was noted for the Northern Atlantic in early 90s when Oak Ridge National Lab had very high computing power, and they showed that it's only when you have very high resolution you get a branch of the North Atlantic current which forms. So this is observations which shows this branch of the current which is not reproduced even when you have 0.2, and they were able to reproduce that only when the resolution was brought down to 0.1 degree, in spite of the fact that the Rossby radius of deformation there is much smaller. So the same model also suggested that even in the Indian Ocean, the eddy activity could be very high, and that is particularly high in the eastern side compared to the western side. So we have been trying to improve the model simulation, and this is an example of our ongoing work. And this model, I must say, this is slightly different from what I showed you so far. This model is called the ROMS. This is a regional ocean modeling system. It's the basic difference is that unlike MOM, which follows a Z coordinate in the vertical, this one follows a terrain following coordinate. So this is a comparison at one particular location where we have some observations. So there are 4 curves in this graph, and 2 are from the model and 2 are from observations. So this green observation is from satellite, green line is observation from satellites, and this black is in situ observations. And the 2 bottom lines are from the model. And one model has a resolution of 25 kilometers, and this one has a resolution of about 10 kilometers. So you can see that when you look at the observations, between observation itself, there are departures. And the model has a bias in that the model simulation is about a degree or about 1.5 degrees cooler than the simulations. Now, I must tell you that the performance of this model is slightly poor compared to the model which I had shown you earlier, simply because the kind of tuning that we modelers generally do has not yet been done. But the reason to do this is that this is the model which has been selected to be a forecasting system for the Indian Ocean, which is being tried at INCOIL. So the efforts to improve the simulations are in progress. Now, coming to the third point, that is the deficiencies of the forcing function. And this is an example from a paper by Schiller and Godfrey in 2003. The forcing that we use is kind of limited because it depends on the availability of data. So that data over the ocean can come either from satellites or from reanalysis systems of atmosphere. So they have limitations both in terms of temporal and spatial resolutions. So particularly when it comes to simulation of the sea surface temperature, the solar radiation is very important. And we often do not resolve in ocean models that particular forcing in terms of a diurnal cycle. So this is an experiment done by the Australian team where we looked at the effect of diurnal cycle on ocean models, and they found that you can have a difference of about 0.4 in simulating the mean temperature if you do not include the diurnal cycle. And please remember that the typical errors that we have been getting in our model is about 0.5. This is not to imply that the complete error would go away with including of the solar radiation because the system is nonlinear, but there is a possibility of improving the simulation by refining the forcing fields. Now coming to the last part of my talk. So at some stage we did try to improve the simulation of the regional ocean modeling system by assimilating Argo data. This was done by part of a master's thesis by a student who since went to the Scripps Institute of Oceanography to do his PhD. So we did not continue on that later. So what he did was to take the regional ROMs for the Indian Ocean, and this is the data that was available from Argo floats at that time. These are autonomous floats which go up and down in the ocean and measure temperature and salinity and report to the satellite. So each color denotes to one float, and the locations are where the data is available. So this data was taken for one particular year, and then it was gridded by an objective mapping onto the Indian Ocean, and then using a simple optimal interpolation procedure, the model was run with and without this assimilation scheme. So, so with that, what he found was that, of course, the assimilation certainly improves the simulation, and this is the observations which has not gone into the model, and the top is without assimilation and the middle one is with assimilation. So the model had, at that time, the model had a strong bias that the model temperature was very warm, and this was primarily due to the deficiencies of forcing fluxes which was used at that time. So the model temperatures were very warm. And when we did assimilate this data, that simulation did improve considerably. And the summary of his work is in this graph, which shows the RMS error between model SST and observed SST. So he particularly noted that if we did not have assimilation, the error grew rapidly during the months of February, March, and April. And this is very important for the Indian Ocean, because it is during those months that the Indian Ocean absorbs a large amount of solar radiation and warms very rapidly. So if there is significant errors in the air-sea fluxes, that can grow to a large extent. So this particular simulation, what we learned is that we need to improve the forcing of those model considerably if you want to get towards higher resolutions. I mean, higher performance. Now, the observing systems of the Indian Ocean has grown tremendously since we did those experiments. We have then we had only one ship. Now we have several ships which collects a large amount of data, particularly along the coastal region of India. And we have a satellite, actually more than one, which gives ocean parameters like winds and ocean color. There are these buoys deployed at several locations over the Indian Ocean, and the Argo program has grown. We have nearly 200 floats profiling, and with a much larger coverage than we had grown earlier. So this is really a challenge to ocean models to develop methodologies and approaches to assimilate this data into the ocean model, so that we can look forward to an ocean forecasting system that is reliable and is useful to the communities. So that's our group on ocean modeling. So we have Nima is our postdoctoral fellow, Ambika is doing PhD, Jafar and Tushar as master students, and Kiran, Srija and Sandeep are working on ROMs. So our collaboration on ROMs with INCOIS is with the Francis, and we also have collaboration on MOM with NIO with Shankar and his students Abhishek and Ramya. And we also have a collaboration to assimilate Argo data into the ROMs using Argo data with Amit and Jaman. And there is a lot of space between both sections. So you're welcome to join. Thank you.
RMSE diagram.
Which one?
RMSE. You showed the assembly. Yeah. So this RMSE of the red one is the analysis RMSE with the analysis after the analysis and with the observation.
Yeah, these are from two runs. In one run, Argo data is assimilated. Okay. In the other one, Argo data is not assimilated. Okay. So the blue is the curve without assimilation, and red is the curve with assimilations. All we have done is the RMS error between the TMI SST data. Note that this TMI SST data is not used in the assimilation. It's an independent data.
Okay.
What we have assimilated is in situ data using Argo.
Okay, thank you.
Variation of SST, TMI SST, this is model SST. For that, what type of software portion you had used in that? Yeah.
Is it this one?
Yeah, this one. So the green one is your TMI,
Yeah.
and the dashed line is your Rama GUI.
Right.
So that was forced into the model. This is the model result, or
These two are observations, and these are model cells. This blue curve is a model which has a resolution of 10 kilometers, and the red curve is a model that has a resolution of 25 kilometers horizontal. Otherwise, the models are identical.
but when you use because you will not be having observations everywhere.
Right.
So you may be using software portion from analysis. Okay. So we have actually now developed a methodology to derive software variation. That software variation over linear distribution from used distribution Metaset or calculus. So real time data you can get from our data that I will be having on presentation now. So that will be helpful for you. That software variation it is as accurate as the JVAC software.
Yeah, it's one of my students is working on this using satellite data using, so we'll talk to you.
Because we have one of our colleagues because they have used that data for this model, this ocean model. They found that the SST variations are captured much better as compared to that from software variation from sensor.
Sure.
We use satellite software variation, get much better result as compared to in-service software variation.
That's very useful information. Thank you. I will look forward to your talk. Yes. Right.
Any other questions?
That was done in 2005. So that was a much coarser version of the model. So that's why the simulation of SST has, well, my philosophy of my personal approach was that one should do as much as possible with refining the model before getting into data. So that's why we step back a little bit before going into data assimilation. And we did refine the model considerably since then. So it did improve. So the next step would be to insert the assimilation package that Amit and Jaman are working on, and so that it will be useful for the broadcast.
Thank Vinay and everybody else in the morning.